Okay, today we're talking about Chapter 4, Section 2. And this section is one of those awkward sections, kind of like how we did the difference quotient, and then we learned the immediate next section, how we can get the derivative without having to do that extremely long difference quotient. One moment. Sorry about that. Been a little under the weather here lately. Anyways, what I was saying is, today we're going to be doing pretty much that the difference quotient, right? And then the very next section we're going to figure out a faster way to do things, and I have to keep that in my head that we need to learn this stuff, but I also at the same time we get there a lot quicker. So let's go ahead and let's snip this as well as what our section is. Put it on the front here. Alrighty, so integral calculus. Okay, that's what we're into now. We're into integral calculus. We were doing differential calculus with derivatives. Now we're doing integral calculus with antiderivatives or integrals. Studies the accumulation of units as the input variables increase. So for example, suppose a jogger maintains a constant velocity of 5 miles per hour. So as she runs, she accumulates distance. After 1 hour, she has run 5 miles. Between the first hour and the second hour, she runs another 5 miles because she's keeping that 5 mile an hour pace. So that for the first 2 hours, she accumulated 10 miles. Right? This is what the antiderivatives uses as the areas does. Right? So real quickly, the derivative, if you recall, what the derivative is the tangent line on a graph, the slope of the tangent line. The antiderivative is going to be essentially the area under a curve. Okay, and this particular section we're going to find the area under a curve in a not so precise way. And of course, like I said, the next section is where the precision is going to come in. But it's important to know the ideas and concepts here. Okay, so I'm going to one ABC. Okay, so I'm going to snip these graphs, and then we're going to solve them. So these graphs are pretty handy. All right, so looking at the problem, let's start up here. So Emma drives her motor scooter at 15 miles per hour for an extended period of time. Okay, so we don't know, we just know that it's extended miles, not, it's an extended period of time. So question A reads, how far has she traveled after 1 hour? Okay, so that's not too hard to do. We can do this in our head, but let's look at this in terms of the graph, in terms of the area under a function here. Okay, so um, I probably should not have. Let's see. Yeah, let me re-snip this first graph because I didn't actually get the x-axis here. So let's go back. I snipped off an important part of the graph. Alrighty, so here we go. So looking at the graph, all right, this is just a very simple graph, and we see that the x-axis is obviously just time in hours, and then the y-axis is the velocity. Okay, well she's traveling at a constant 15 miles per hour, right? And then of course we just go along the x-axis for time in hours. So how far she travel after 1 hour? Again, this is arithmetic you can do in your head, but we're gonna try and look at this in terms of a graph real quick to really understand the area under a curve. All right, obviously this isn't a curve, it's just a graph, but if she's traveling at 15 miles per hour, we have just a function that's a horizontal line at 15, and then what we're going to do is we're going to fill in the rectangle underneath this curve, this line, and then that area is going to tell us how far she's traveled. Okay, and again, if she travels 1 hour at 15 miles per hour, we know that she travels 15 miles. Okay, but let's look at this in terms of the area of the curve instead, though. Okay, so the area of this box, okay, I keep saying curve mainly because we're going to be dealing with curves, but this linear equation, all right? So what is the area of this rectangle here, right? Well, the area of a rectangle is just simply length times width, correct? Right? Well, what is the width? Well, the width is just 1, and what is the length? Well, that's 15. And 15 times 1, well, that's obvious. It's just 15. So that's one way to look at it. We looked at it graphically. And of course, like I said, we could do this in our head. So she traveled 15 miles. Okay. B, how far has she traveled between the first hour and the second hour? Okay, well, kind of the same thing. Um, we could do this in our head because I mean she's traveling at 15 miles per hour in the hour, all that good stuff. Well, again, looking at the area of this rectangle, from 1 to 2, that's 1 unit, and then vertically it's 15, right? So again, the width is 1 and the length is 15. So again, she traveled 15 miles in the second hour. And then C, how far she traveled cumulatively over the first 2 hours, right? Well, again, easy math, but let's go ahead and do the arithmetic here, looking at the area of this rectangle. All right, well, from 0 to 2, that's 2 units, and from 0 to 15, that's 15 units. Again, length times width, so 2 times 15 is 30, so she's traveled 30 miles in 2 hours. Okay, and let's fix that D. D. So what function f of t gives Emma's total distance traveled after t hours? Well, pretty easy to see here. It's just going to be 15t, right? She travels 15 miles per hour, and so 15 miles. And let's actually put this over on the other side so we can make a proper um, function notation here. F of t is just going to be 15t. Okay, so obviously the area of a rectangle is pretty easy. Well, we did length times width, but I mean base times height, no big deal. And so let's go ahead and snip this along with our problem. Okay, so now we're going to do this a little weird because I don't want to snip the solution. So actually, you know what? This can have its own page. All right, so rectangle is base times height, and then the area of a triangle. All right, you probably already know this. You went through geometry. If you don't know this, then you are going to very quickly recall it because I know you've seen this before. So the area of a triangle is half the base times the height. Okay, so I feel like these are pretty easy um, area equations. So I'm just going to keep that. I'm just going to let it have its own page. All right, so next up, what we're going to do is give this a new page. And again, we're going to look at the graph of this problem. Okay, so the first example, we just had a horizontal line. This time we don't have a horizontal line. So uh, what, well, hang on, let me just do this. 1 second. Alrighty. Sorry for the continued breaks there. But anyways, so let's go ahead and read this problem, and then we'll look at the graphs here. So a toy drone flies in a straight line, and its velocity t seconds after takeoff is given by v of t is equal to 2t, where v of t is in meters per second. Okay, so um, our graph here is going to be the function 2t. So we see our line here, and that's a function showing the takeoff of our toy drone. Again, the horizontal axis is the time in seconds, and the vertical line is the velocity. So we're traveling at a constant velocity of 2t here. Okay, so in the first example, it was pretty easy because all we had to do was just find the area of a square. Okay, this example, we're gonna get a little clever once we get past this triangle, and we'll see what I mean by that here in a minute. So let's find the distance of that the drone has flown after 1 second. So let's look at our graph here. All right, this graph, and looking at that graph, we're just going to try and find the area of that particular triangle underneath that graph. All right, so the shaded area, all right, so if you recall again, the area of a triangle is half the base times the height, okay? Well, so it's going to be 1/2 times the base. Well, what is the base? Well, the base is just going to be right here, and it's just 1, right? From 0 to 1 is 1 unit, so it's going to be half of 1 times the height. Well, what is the height of this triangle? All right, well, it looks like it's 2 units. Okay, so it's 2 units. Well, 1/2 times 1 times 2, that's just going to be equal to 1. Okay, so the drone has traveled 1 meter. Okay. Now we're going to have to get a little clever with b, and of course you can obviously see what we're trying to do here. But so we want to find the distance the drone has flown between 1 second and 2 seconds. So we're now looking at this particular shaded region. Okay, well, this shape that we see is this, and more or less. Uh, and the thing is, we don't have a nice, pretty formula for the area of whatever that shape is. All right. Instead, what we're gonna have to do is we're gonna have to turn this into two shapes. Right. The first is going to be this triangle, and the second is going to be this rectangle. Okay. And then we're just going to add those two areas up together. Okay, so let's go ahead and add up the area of the rectangle first. And let's just go put that in green just to kind of correspond maybe. All right, so looking at this, again, the area of a rectangle is just simply base times height. Well, the base times height here, if we look, looking at this rectangle here, all right, well, what is the base? Well, the base, from 1 to 2 is 1 unit, so it's going to be 1. And then the height it's going to be 2 units, so times 2. So it's just going to be equal to 2. Right? And in the blue, we're going to do a triangle. The triangle, what is the base of the triangle? It's also 1. Right? So it's going to be 1/2. Again, it's half the base times height. So 1/2 times 1. And then what is the height here? Well, the height is going to be 2 units. So we're just going to do 2 here as well. And then so 1/2 times 1 times 2, we've already done something like that before. That's just equal to 1. Okay. Well, the area of the rectangle is in the green. The area of the triangle is in blue. Okay, and like I said, we're just going to add those up. And let's go ahead and maybe we'll just put to this. Area is 2, and the area is 1. And then obviously the area we add that up, we are equal to 3 meters. Okay, so from 1 second to 2 seconds, our drone has flown 3 meters. Okay, now C, find the cumulative distance the drone has flown over the first 2 seconds. Well, it's not too hard. All we have to do is just simply add them up, right? 3 plus 1, 3 plus 1. So it's flown 4 meters. So C, 4 meters. Okay, so all we're doing here is just simple geometry. Simple geometry, and we're just finding the area under a curve. So let's we'll put this in the notes. Not a big fan of example 3, so we're just going to skip that one for right now. All right, and then we're going to get to the whole point of this section, the Riemann summation. So we in this particular class we've been getting introduced to a lot of notation that you see in math movies, right? Well, here's pretty sure the final notation that we're going to be covering in this particular text or in this particular class, and this is the Riemann summation. Okay, so the Riemann summation is basically what we've done so far is we've only, if this was example 1 or 2, what we've only done is we found the area of just one rectangular triangle at a time. Okay, and of course we've also had pretty easy functions, right? We've had linear functions, whether it just be a horizontal line or the drone just going shooting straight up. But what if we have a curve like this? All right, how do we find the area under this curve? Well, uh, and this is where the whole point of the difference quotient leading into getting the derivative kind of plays in, because looking at this graph here, we have these 4 rectangles. Well, notice how we're not going to fully get the area under this curve, right? Because we have a blank space here that's not covering the area. We have a blank space here not covering the area. And of course, we're going over the curve here, and so it's going to be it's not going to be exact, but we're going to show how this is. Um, how we find the area under a curve. Again, this is the hard long way, and not only is it the hard long way, it is inexact. Anyways, so looking at this, we have x sub 1, x sub 2, x sub 3, x sub 4, and what we would do is we're going to find the area of each one of those, and we're going to add them up, right? So we have the function of x sub 1, and then the delta x, the change in x, which is, for instance, from x sub 1 to x sub 2, we don't know what these x's are, but in the previous examples, the distance was just 1. Okay. But anyways, and so we add all those up, and then we end up with our Riemann summation formula here. Now, this notation is probably new to you, so let's go ahead and maybe break it down a little bit before we continue. And let me see, did I snip that too soon? No, okay, good. Okay, so this 5 down here just corresponds with the next example. But anyways, so let's go ahead and let's make this a large version of the Riemann sum, so we can is equal to 1, and it has a 4 up there, but I'm just going to put an n for right now, and then f of x sub I, and then delta x. Okay, so the way that the Riemann summation notation works out, that delta x looks horrible. It's delta, that looks the same, whatever. Okay, so is you start at whatever this number is. Okay, and in this particular case, we start with I is equal to 1, so we would say x sub 1. And then we would go all the way, we would add the notations all the way to n. And I guess the next example really shows what I'm trying to say here. So without getting too confusing, let's just go ahead and go to the next example, and we'll really see how we get there. Okay, so in this particular example, we see that we start the number down here, right? This is I is equal to 1, so we're going to start at 1, and so x sub 1, and we're going to go all the way to x sub 5, which is the top, what the top number is telling us, and that's really it. Okay, so if I were to, and I'm going to, I guess, go ahead and write this as in Riemann notation. All right, so we're going to write that, which, by the way, this is I'm pretty sure it's the Greek letter sigma, and we use sigma to represent summation. All right, summation basically is just summing everything up. Okay, so let's go ahead and let's color coordinate this a little bit. So we're going to put the 5 up here, and let's put this I is equal to 1 right here. And then we can just, I'm pretty sure we can just do this. And then delta x. Okay. So the way we begin this is we just start with where I is equal to 1. Okay, so we're gonna write all this, except what we're gonna do is we're just gonna change the I into a 1. So we're gonna say h of x sub 1 delta x, and then we're gonna do plus h of x sub 2 delta x, and well, so on. And I'm not going to put a break there. I don't like that big break there, but I can't write too small, so I'm just going to go ahead and snip what the textbook actually has. It's not much, and so let me make sure I make these ellipses very apparent ellipses. Okay, and then it goes on, and of course we see our solution in the nice handy dandy textbook format. So this is how the summation formula is written, how we go about it. Now again, don't be intimidated by this h and this delta x. We're going to cover that here in a moment. But this is just giving you an idea of, you start with the number down here at the bottom beneath the summation symbol. You start with the number down here, and you go all the way to this number up here. So we go all the way to 5. Okay. So for instance, if this I was a 3, then we would just then we would write 3 here, 4 here, and then we would have stopped at 5. Okay. So now we're going to get into some of the good stuff. Alright, so this problem reads, consider the graph of f of x equal to the square root of the quantities of 4 minus x squared over the interval from 0 to 2. This is a quarter circle of radius 2, so use a Riemann sum to approximate the area under the graph using 4 equally sized subintervals and then 8 equally sized subintervals. So here we have a picture of what 4 equally sized subintervals look like. All right. Then use geometry to find the area under f over 0, 2 and compare the values to your approximation. So, okay, so we'll just do this in order. All right, so if we're going to use a Riemann sum, all right, we're going to have 4 subintervals here. So we're going to have to figure out what the delta x is, what the change in the x is going to be. Okay, so in order to do this, let's go back and look at the formula to let you know I'm looking at. All right, so again, notice how our summation formula here, we have this delta x, and of course in all these, let's make this a little bit bigger. Okay, so notice how in all these terms, they all have delta x. Okay, we're just, first thing we're going to do is find the change in x. So in order to find the change in x, it's pretty simple. Just go ahead and let's go ahead and denote what the change in x is going to be. All right, so the change in x, if we're trying to find 4 equally sized subintervals, so we're going to do the 4 equally sized subintervals first, which is right here. So what is the change? Well, looking at the interval given to us is 0 to 2. Okay, so what we're going to do is we're going to take the difference of them and then divide it by the number of intervals. Okay, so we're going to do 2 minus 0, which is 2. So the change in x will be 2 minus 0, and then divided by the number of subintervals that we want. Okay, so it's going to be 4. So each one of these rectangles are going to go out 1/2 on the x-axis, and we see this down here. right? We're just making a rectangle from 0 to 1 half, from 1 half to 1, from 1 to 3 halves, and 3 halves to 2. That's all we're doing, okay? And so that's our delta x. Next, what we're going to do is figure out, sorry again. Next thing we're going to do is figure out what the functions are at those x values. Okay, so what we're going to do is, man, I'm going to run out of room here. Let's go ahead and let's snip it right here. Okay. All right. So I didn't want to make my notes look messy because I was going to have to write this entire line here, and I don't know if I could have just fit that there. But we will thoroughly talk about it, very thoroughly talk about it. So we got our delta x here, and notice how in our summation we have that delta x, which is 1 half, 1 half, 1 half, 1 half. We put it in each single term, just like we see here, delta x, delta x, delta x, delta x. Okay. So next thing we're going to do is notice how, going back to our function here, we have h of x sub 1, h of x sub 2. Now, if the h throws you off, you could think of it, just as what we're used to calling functions. You could think of it as f of x sub 1, f of x sub 2. Okay, it really doesn't matter what you call the function. It's just as long as you know that it is a function. So the way you set this up is you say the function at 0. Again, our intervals they go up in they go up by half. Okay, so looking at the function from 0 to 1 half, from 1 half to 1. And we're going to do this 4 times because we're wanting 4 equally sized subintervals. So f of 0 times my delta x, f of 1 half times my delta x, f of 1 times my delta x, and then f of 3 halves times my delta x. Again, we're just going up 1 half. We see the pink here, we're just going up 1 half each time. Okay. Well, we are familiar with factoring. We notice how we have 1 half in each one of these. And by the way, you can do this every single time. You factor out that delta x. Okay, so when you factor out the delta x, you're just simply left with f of 0, f of 1 half, f of 1, and f of 3 halves. Well, by plugging these into the calculator, right, so f of 0, we can do this in our head right now anyways. F of 0, 0 squared 0, so 4 minus 0 is 4. The square root of 4 is 2, so we have 2 here. Right? And then f of 1 half, well, 1 half squared is 1/4. 4 minus 1/4 is 3 3 quarters, and then the square root of 3 3 quarters is 1.93649. And then we do that for all the terms. Okay? And of course, we add that up, multiply it by 1 half, and we end up with this number here. Okay, now what I said before is that this particular method is inexact. All right, and I'm just going to go ahead and jump to kind of the last part of this example to really show why this is inexact. All right, so let's go ahead and look at what this is. Okay, so this is a function. All right, it creates a circle with a radius of 2. Okay, so real quickly, what is the area of a circle? The area of a circle is pi r squared. Okay, well in this particular case, well that's not it. Our radius here, right, is going to be 2. So the area here is going to be pi r squared. Well, 2 squared is 4. So my area here is going to be 4 pi. Okay. Well, since this is just a quarter of a circle, okay, I'm going to take the area of this entire circle, and I'm going to divide it by 4, okay, or multiply by 1/4. Same thing. Right. And by doing that, I get, so 4 pi divided by 4 is, oh, that's interesting, is 3.1415, right? It's actually pi in this particular case. Okay. So this 3.14 is the actual area of this underneath this curve. Okay. So in our example of using 4 subintervals, we got the number 3.49. okay, which is quite a bit of ways from 3.14. All right, so keep 3.14 in mind. Again, it's pretty easy, I think. So let's go ahead and do the second part where we divide it up into 8 subintervals. Okay, so we can start here. Hang on a second. Okay, so this is the second part of the section. And again, this is just the same arithmetic, except this time we have 8 subintervals, and my delta x is going to be basically the same. Well, you do this for every single time you do the Riemann sum. All right, you look at your interval, okay, and then let's see, let's do it this way. If your interval, hang on, if your interval is set up in this form, okay, AB, all right, that's up here, AB. Well, then all you do for the top of the delta x, this right here, is obviously just B minus A. Okay, and I don't think that actually said anything in this text about it, but we're talking about it now. All right, you do B minus A divided by how many subintervals you have. All right, so in this particular case, B minus A here is 2, and then we're dividing it into 8 equal subintervals for the second time, and it's 8 2/8 or 1/4. So let's go ahead and erase all that and go back to that part of the problem. Okay, and of course we do indeed see it's equal to, my laser pointer, we do indeed see that is equal to 1/4. Okay, and so you start at 0 and you go up a quarter each time. Okay, so 0, 1/4, 1/4 plus 1/4 is 1/2. 1/2 plus a quarter is 3/4. And of course, our delta x, same as before, stay the exact same. 1/4, 1/4, 1/4, 1/4. Okay, and of course we do the arithmetic. Again, you can do this every single time. Just go ahead and factor out the delta x, which is 1/4. I don't know if you guys can hear that, but there's some beating going on with my neighbors. So f of 0 is, and again, we can do this in our head. We did it before, right? 0 squared is 0. And it's 2. And then, of course, you take the function at each one of these values, and you end up with all these numbers. Okay, doing the arithmetic. Yeah, there's no way I could have fit all this on the screen. Doing the arithmetic here, we end up with 3.33. Okay, so by using 4 subintervals, right, using 4 of these rectangles, we ended up getting an area of roughly 3.5. Okay, when we used 8, and hang on, I gotta get rid of this. Whenever we use 8 subintervals, we end up with roughly 3.3. But we said that the actual value is 3.14. So what good is this, right? If we're getting things that are pretty far off, I mean, matter of fact, let's just percentage wise, that's what 19 no 0.19 divided by 3.14. We're talking about 6% off here. Okay, so what good is this? Well, truth is, it's not. And the reason why is because, like I said, in the next section, we're going to figure out a better, faster, quicker way to do this. Not only is it better, faster, quicker, but it's also exact. So it's better in every single way. And like I said, that's why this section is one of those awkward sections that, we show you how to do things or where things come from, but then we show you a better way. Okay. All right. So. Example 6 is more the same. All right. Next up, we're going to go to the definite integral. Now, the definite integral, this is going to lead into the next section, which again is going to be the next lecture, where we actually get the exact solution here. Okay. So these are called definite integrals. Did we define indefinite earlier? Let me see. No. Okay. So that's awkward too as well. All right, so uh, introducing the concept of definite integrals. So definite integrals, all right, if something is definite, then we are for sure, right? We are pretty sure, we're definitely sure that something is true. And honestly, that pretty much leads into what I've been trying to say this entire time. So the key concept being developed in this section is that the more subintervals we use, the more accurate the approximation of areas become. Okay, so let's go back to the previous example. We said that going from 4 subintervals, which is about 3.5, and then we double that to 8 subintervals, we get to about 3.3. All right, we're still far off from the 3.14 that we said that this area is. All right. Well, the thing is, if we subdivided this section into 100 subintervals, okay, that would be uh, ridiculous. We would have this summation notation, and we would go absolutely crazy there. Um, and I just realized, yeah, even the text has to continue on to get those 8 subintervals. But the more subintervals you have, the closer you get to the actual area. Okay, but we don't have time to sit around and figure out the area of 1,000 rectangles. But the more rectangles you have, the closer and closer you get to the actual size. Well, where are we at? As the number of subdivisions n increases, the width of each rectangle, the delta x, decreases. So if n approaches infinity, n being the number of subdivisions, then delta x approaches 0. Right? The change in x approaches 0. So the closer and closer we get to 0 with our intervals. So the definition here, so if we let y is equal to some f of x, okay, so we have some f of x, and that's just pink line right here. So y is equal to some f of x, okay? It's continuous, it's non-negative, and it's over the interval a to b, some a to b. Again, just looking at this example, we have some interval there. A definite integral as is the limit as n approaches infinity. Again, n in our case being the number of rectangles, right? Um, I don't feel like I said that better or good enough, but if we had 1,000 of these rectangles, we would get closer and closer to 3.14. If we had 10,000, we'd get even closer. If we had 1,000,000 of these, we'd get even closer. Okay, but we wouldn't be exact. We would just be closer. Right. So as we approach that infinite number of rectangles, we get a better approximation of the area. Okay, so the Riemann sum of the areas of rectangles under the graph over a to b. Again, that's just the interval. So the exact area of what we've been doing so far in this section, okay, can be equated to something that's, in my opinion, well, I say my opinion, in everybody's opinion, a lot easier, and that's just doing the definite integral, right? So I would much, much, much rather do the definite integral over some interval than figure out or then sum up 1,000 rectangles. I honestly don't think I've summed up any more than 8 rectangles in my entire life, and that's only because every single time this concept is introduced, it's an example like this one that we just did, where you summed up 8 segments, and that alone takes too much time. But we can sum that up, I guess no pun intended, with just doing the integral. Okay, so what do I mean by that? Well, unfortunately, this text doesn't really tell us, doesn't really get there to it. But what I'm going to do is kind of give an example here. Well, no, I don't think I should. Right. I was going to go ahead and do the indefinite integral for the last section, or for the last example, but I don't think I should. Ah, what the heck? I don't care. We're going to do it. Okay, so I'm just going to go ahead and snip this and just kind of give you an idea, I guess, going into the next section. So it says find the value of, all right, so we have our integral, all right, and again, the notation here, all right, so let's see, let's go ahead and write this like this real fast. Okay, so this is a notation that we used in 4.1. We're used to this so far, hopefully. Okay, we're introducing something new here, and that's a number down here and a number up here. Okay, well, what that means is obviously, well, let's change this color here to red. Okay, what that means is we're going from 0 to 2. And notice how this is the 0 and this is the 2. Okay, so we're going from 0 to 2. All right. Now, example 7 is the same way we did, we see example 2b, right? We got the area of this rectangle, and then we added the area of this triangle. Okay. Now, again, for something like this, it's not so bad. But I'm just going to, like I said, just give you a little precursor to the next section. So what we do here is we're going to go ahead and integrate 3x um, 3x plus 2. So if we integrate that, we end up with a 3x squared over 2 plus 2x. No. Whatever. We'll do it now anyways. I wrestle with this, as you can tell. So this, and of course plus c, but we're not going to be worried about that because we have a definite integral. So the way you figure out the area here is you plug in these values, 2 and 0, and you subtract 0 from 2. Okay, so what you'll do is you'll plug in a 2 here, so 2 here and a 2 here. So 2 squared is 4, 4 times 3 is 12, 12 divided by 2 is 6. Okay, so you have a 6 here, and then plus 2 times 2 is 4, so 6 plus 4 is 10. Okay, so we end up with a 10, and then what we'll do is we'll subtract, and let's go ahead and rewrite this like this: 3x squared divided by 2 plus 2x, and then we'll subtract the second part here, which is 0, right? We plugged in 2, which was the top of the notation, and we're going to subtract the bottom of the notation, which is pretty easy to do here, right? 0 squared 0, 3 times 0 is 0, 0 divided by 2 is 0, plus 2 times 0 is 0. So you'd say 10 minus 0, or in other words 10, which is the exact same solution that you'll get if you add up all those, I'll say all those, if you add up the rectangle and the triangle. So, all right, so I don't feel too bad going over this because, like I said, awkward section, it's one of those that get you an idea of what we're about to do, but then we figure out a faster, better way to do it. Whew. Okay, so that, I believe, does conclude today's lecture. Yeah, there we go, section summary. And that's it.